Okay, so linear relations as an example of the simplest kind of relation. So it's here. This one. Okay, so as long as one of A or B is not equal to 0, you have a linear relation. The graph of it is a straight line, and we just prefer this implicit representation of straight lines because it gives you simultaneously all lines, including vertical ones. Remember, vertical lines are not graphs of functions, but this way, if we think of it as a relation, we have them too. Okay, but it is only the beginning because there are relations that are more interesting than that. So let's just go try to visualize some of them. And what I have in mind, well, let's take another look at this. So once again, remember what this represents: the width against the depth of that rectangle enclosure with the fixed perimeter. Okay, so as you can see, so we have all the possible depth from 0 to 100, all possible width from 0 to 100. We took their, multiplied them by we didn't. What we did is okay, so that's not what I actually had in mind. Here's a. Let me make a copy. Let me make a copy. Go away. Go away. Okay, so what I want to do here, I wanna add these together. So once again, depth goes horizontally, width vertically. What I'm going to plot here is their sum. Okay, so remember the relation between width and depth was that they're supposed to add up to 50, so that the whole perimeter will be 100. Okay, remember that? Okay, so let me just write it out. So I'll have here equal to what is this? Row 3, same column. Wait a minute, row 2, same column. Okay, so that's the d value, the depth value, and I multiplied by the same row, column 2. Okay, so as you can see here, I multiply. I wasn't going to multiply. I'm going to add. I'm going to add them. Add. Okay, so once again, the d value plus w value, they're supposed to naturally adapt to 0, but here's the rest of them. Okay, so these are the parameters. So what is half of the parameter? Okay, so if it's 0, 0, then of course they adapt to 0, but you can also see that what we just did, what we saw previously, is whichever adapt to 50. These are the ones adapt to 50. And they happen to be a straight line, so once again, this is an example of a linear relation. Okay? And we just manually add them up one by one to indicate which add up to 50. But you can also see that there is more to it. We could have, well, you see 60s line, there's a straight line once again, 60s. You can see 40s and 30s and 20s. So if you progress diagonally like this, you can see how the perimeter is increasing. Okay, so in other words, we simultaneously see a bunch of relations on this picture of what? So relations are x plus y is equal to 50, but then also x plus y is equal to 60, and x plus y is equal to 70. So all of these are separate, different relations naturally, but you can see them on the same xy plane. Okay, so that's what I want to proceed, but I want to have them all simultaneously, and I don't want to do it by hand. So fortunately, there is a tool for that that Excel has. So it's called Conditional Formatting. So color, I just give it different color like this. Okay, maybe this one. Which one is the best? This one seems okay. Okay, so you can probably see what the pattern is. Do you see the pattern? So try to go diagonally from the top left and to the bottom. What's happening to the numbers and what's happening to the colors? Right, but let's go. Let's start at the top bottom and go diagonally up to into the right. What's happening? What? So from 100, I make so 45 degrees. 45 degrees. I'm going diagonally in that direction. What's happening? They are white and the number is the same. So that's how it colors things. The same numbers are colored the same color. So as zeros are 100s are colored with white. It just happens. But you can see that 90s are colored with something virtually invisible pink. But you definitely can see these are the 50s. They are covered with the same roughly color of pink. So actually, maybe there might be better ones. There are color schemes with more colors, so maybe, how about we try this one? I'm not sure it's any better. So the pattern, unfortunately, is not very pronounced. I was hoping that it would be visible that, like I said, the pattern is of the value of the color stays the same if the value of the number remains the same. So that way we're supposed to recognize here a bunch of straight lines. These are straight lines. They have the same numbers, diagonal lines like this. They have the same numbers and they have the same colors. Okay, so with that idea in hand, I want to look for more complex relations. And so I remove this, so it will be just x versus y. And zoom out. Okay, so let me maybe make it more of these. Maybe what happened here? Okay, so I'm going to have what happened here? Let's spread it. Okay, so let me spread this out if the pattern becomes clearer, if it is bigger, and if we zoom out, maybe it will be easier to see. Okay, so there is some visibility of the pattern. So the change, for the largest change, you have to go diagonal like this, from red to pink to white to light blue, dark blue. Okay, so that's if you go diagonally. What is it? Northwest. If you go northeast like this, then there is no change in color. Every time it remains on the same level. Okay, so you can imagine that. You can even imagine that this is a surface and of the Earth, and when you are going along, so either you're climbing, you will be climbing this way, or you are not climbing at all if you're going that way. Okay, so numbers remain the same if the number indicates the altitude. Okay, so if you go diagonally this way, altitude is not changing and the color is not changing. That's how maps work. Have you seen maps with the colors, right? So that's exactly what those colors are supposed to indicate, the altitude of your location above the, say, sea level. Okay, so once again, you can choose the right direction. You are not going to be climbing at all. Okay, if you stick with the same color, there is no climbing. Okay, so I want to have a more complex relation, and the relation that I'm thinking, what if I replace the sum of these two things with the sum of the squares? Okay, you see what I'm saying? So here that was a linear relation, so I'm simply adding the two values, and this time I want to add the squares like this. Can you predict what's going to happen with the pattern we have here? adding squares rather than the values. Well, maybe it's anyone? Okay, do you see what's happening? What? It is bigger, but can you see the pattern of those curves? Remember, I talked about the curves when there is no change in the value. They are not really entirely not changing, but you can see the curving of the colors. You see it? If you want to stay on the same level, how would you proceed? Say I start over here 2255, 2255, 2255, 2260. So I'm going to be, see over here, I'm going to be circling. I'm going to be circling around. So there is a blue area which is not bounded by a straight line, but rather by some kind of curve, right? So once again, if I want to stay on the same level of color, I will be moving like this. You see it? Well, let me try to maybe make these narrower so the pattern will be clearer. Column width. Make it 4. Too much. Let's make it 5. It still doesn't fit. Well, at least the pattern is clear. So the curving of the white area. Think about the white area as if it is a curve, and you can see how it goes straight and then turns around like this. You see it? Okay, so that is the relation which is not linear anymore. So these all the points that are white, they are related to each other because the x squared plus y squared gives you the same number. So say what is that number? Any number that you can pick, but there is certain change of the value, 20 to 500 to 600. But then if you want to stay on that color, you would end up with where am I going? 20 to 500, 20 to 6. It's here somewhere in between. And then if I'm staying with the same color, the contrast is insufficient in order to see a pattern, rather than the only thing that is clear from this coloring is that it's not going to be, so it's not a straight line, right? So, so if you try to imagine what a surface like that looks like, what do you think it looks like? A surface with the it's like a mountain. Think about a mountain. So the blue one is, say, the height. They are the highest. They're actually the lowest. Okay. So the at the upper left corner, we are at the lowest at 0, and the highest value is at the opposite corner, which is 170 to 140. Okay. So and that is the brightest red color. Okay. But what about the rest? Let me zoom out, maybe. I guess you can kind of see how the blue is not bounded by not by a straight line, by a curve. Well, long story short, it is a circle. Okay, so what I'm talking about is the relation being what? So the relation is x squared plus y squared is equal to, say, 1. X squared plus y squared is equal to 10. X squared plus y squared is equal to 100. So these are all of them we're seeing on the same xy plane. Okay, so so in each of them is colored by a different color. Okay, so you can almost you almost then do not see the difference in the color because, well, it's showing a subtle change. But if you can imagine that the numbers are exact, then you can understand why this is a circle. But let's try to do some algebra instead to begin with. That might help. So let me pick this one. Okay, so plot the relation. Okay, we plot the relation. Remember how we are plugging in xy. Xy is given on the xy plane, and then we have a question to be answered. X squared plus y squared is equal to 1. And there are two answers, yes or no, possible answers. Okay, and then if it is yes, we plot this point, xy. If the answer is no, don't plot. Okay, so you have to go like this, which is pretty much what we're doing. We're going like this, on and on until we are, until we reach the, until every point is covered, and then the most points will be plotted, and some of the points will be plotted, some will not. Okay, so if we try to do it by hand, probably a good idea to start with that. I will have immediately a lot of points that are not on the graph. Okay, so for example, if I try say -2 over here, so x is equal to -2, x equal to -2, y equal 0. Okay, so the answer is no. If I, on the other hand, I try here, 2, x equal 2, y equals 0, once again, no. 0, 0, once again, 0 and 0, once again, no. But if I take 1, 0, then it is a yes. 1, x is 1, y equals 0, so it is a yes. Okay? Here is another one. X is equal to -1, y is equal to 0, also yes. Yes. Okay, so I plot the green ones and red ones that I discarded. So can you suggest any other points that I should try? So the sum of the squares is 1. Okay, so if x is 1, y is equal to 0, then we have 1. Okay, what else? What else can you think of?
0 and positive 1.
0 and positive. So you flip x and y. So this point over here, x is 0, y is 1, so it's once again a yes. And another one right over here, x is 0, y is -1. Once again, it is a yes. As you can see, they start to sort of show a pattern. So my point is here somewhere. Okay, so as you can see, if we're too far from the origin, it is a no. Okay, we had two squares, and they are just too large. They do not add up to 1. If they're too close to 0, once again, we take the sum of their squares, and they do not add up to 1 again. Okay, but the points that are just right distance from the origin will satisfy this restriction. So points are not too close, not too far from the origin. Those points that will be plotted. So you can easily think of more points, say 1/2, 1/2. If I take the squares, it will be 1/4 plus 1/4, which is 1/2, which is not equal to 1, so no. So another point over here. Then similarly, I pick -1, -1/2, -1, -1/2, -1, -1, -1/2, -1/2. All of these points will also be a no. Okay, so, and then if I take a 10 and 10, large points really far away from the origin, they also will be known. So this is just trying them one by one. It's very hard because there are infinitely many points, and you cannot really effectively cut them into small pieces so that you can easily, you have to go left, right, left, right, left, right, like this. And then you have to check out every time by hand. So that's why using software for that purpose is probably a good idea. I just want to have these numbers to be slightly better. Better fit our purpose. So, okay, so I'll start. What is going on here with this? Okay. I think I'm okay now. Okay, so I'll start with, say, -2, okay? And then I'll add 0.1, okay, yeah, 0.1, okay? Right. Okay, and same here, plus 0.1. So rather than going 1 to 10 units at a time, I go 0.1 at a time. Okay. Okay. So now the pattern is clear. So what I was describing once again, either you're too close to the origin and then you do not adapt to 1, or you are too far, and that's when you have red, and then once again you don't adapt to 1. You can see some of the 1s appearing here. You can guess that these are definitely the points on the graph of my relation right here. Anything close to 1, and you can also see they are pretty much all white, either very white or somewhat white. Okay, so that reveals the pattern of circular set of points on the xy plane, and that's what the graph is. The only so that's how we do it. Let me give you some more points here. Okay. Let me narrow this down. 4. Okay, so because there is no proportion, so it might be stretched out a little bit, but you can see that the difference of this pattern with the previous pattern, which produced straight lines, and this one produces circles. Okay, so the only thing I am not able to show you here is that it's not just a circle. It is in fact it's not just a circular pattern. It is in fact a curve. It is literally a curve. A circle is a curve, and because we're doing it on those cells, the accuracy does not give us the feeling of that it is a curve. So that's the question to be addressed. Is this a curve? Is this a curve? Well, the difference is obviously this is a curve, and what we see on the picture is looking something like this. So the question is, does it have the width or not? So this is a curve. This is not a curve. So just doing it with Excel does not really tell you the whole story. It tells you that there is some circular pattern. This is too far, this is too close, and somewhere in between there is some ring. Best you can tell from this picture that this is a ring. So that white ring surrounding the origin is the graph of our relation. So to have the answer for sure, you have to do more of this. So how to answer? The answer is by means of so find a function, if possible. Okay, so first of all, remember that functions are relations, but not all relations are functions. So the good news is then whatever we say about relations also applies to all functions, not necessarily vice versa. So if we are trying to find a relation for a function, it means simply that what? Solve for, say, y. So x squared plus y squared is equal to 1. I want to solve it for y. What happens? What do I get if I solve for y? How do you solve for y?
Put y
What?
on one side.
Yeah, put y on one side. Okay, so let's just do that step by step. You don't have to do it in your head. It's probably just a bad idea, bad habit. So I'll just I leave y on one side and then pull everything else to the right-hand side. So I have y squared is equal to 1 minus x squared. Okay, so that's step number 1. All y's on the left, and nothing else is on the left, only y's. Okay, all the x's are on the right. And then the next step is I have to isolate y from the rest. I want to have what differentiate a function from a relation in general is that I want to have y equal something. I take exactly. So let's take square root of both sides. Okay. So on the left, presumably I'm getting y, and on the right I have a square root of 1 minus x squared. What did I skip? What? Yes. Yeah. So how do it is 2 answers? So what should I put there? Plus or minus, right? Okay. So okay. So have we found a function for it? So we try to find a function that would represent our relation. So have we found it? Is this a function? Well, do you remember how functions operate? So there's input and there's output. What's so special about this relation between input and output which will make it a function? So x is the input and y is the output. Yep. To what question?
Is it a function?
Yeah.
It
is. Is it?
I think it is.
Well, why do you think it is?
Because it's got an input and output.
It does, but what does plus or minus does worry you at all?
But the x have a range.
Yeah.
So 1 minus x.
No, you mean in the domain?
Yeah. L1 should be smaller than. It has to be bigger than 0.
It is. The domain is a concern, sure, but once you have a function available, you'll know the domain for sure. But is it still a function? What about that plus or minus?
Not a function
because
you can have 2 inputs for 1 output.
Vice versa.
Okay, so you can have 2 outputs.
2 outputs for 1 input,
okay.
right? You see it?
I was on there.
So when you put that plus or minus creates 2 outputs
Okay.
for the same input. So if I plug in 0, for example, I will end up with 2. 1 minus 0 squared, plus or minus. I have plus or minus 1. 2 outputs for 1 input. Okay, so as it is stated, this is not a function. So it can be often more subtle, but this one is very explicitly not a function. Whenever you see plus or minus, it is an indication that probably this is not a function, because that plus or minus, they appear simultaneously, and you can pick plus or minus or both of them, so that for the same x, you plug in your x into your formula, and you end up with 2 numbers, so 2 outputs. And you can see that. Well, let me do it. So x and y, I take negative 1. How about negative 1/2, 0, 1/2, and 1? Okay, so all of these are within the domain as 1/2, 1/2, and 1. Okay, so I plug these 5 into my formula. I'll have 0. If I plug in negative 1/2, I'll have, well, let me write it out. Let's not rush things. So I have plus or minus square root of 1 minus negative 1 squared, or I end up with plus or minus 0. Okay, so that is the good news, would be good news, because we end up with 1 answer. Even though we have plus or minus, sometimes you might get 1 answer. But if I plug in negative 1/2, I have plus or minus 1 minus negative 1/2 squared, square root, which gives me, so 1 minus 3/4, or square root of plus or minus square root of 3/4. Okay, so 2 answers. Same with 0. Plus or minus 1 minus 0 squared gives me plus or minus 1. It's 2 again. 1/2 plus or minus 1 minus 1/2 squared gives me once again plus or minus square root of 3/4. At the end, 1 minus 1 squared gives me only 1 answer. That's good news. Okay, so if this algebra does not speak to you, you can do it this way. You can just plot them like this and use arrows. So say negative 1, negative 1/2, 0, 1/2, and 1. Okay, so these are x's. And then you have a bunch of y's here. So say, and then you end up with something like this. So there are 2 arrows originating from some of the inputs. 2 arrows originating, and they are in 2 different locations. These are the 2 outputs that create a problem for us, because that's not a function anymore. Inputs on the left, these are x's, and some of the x's produce 2 outputs. When it is algebra, it is plus or minus is one of the indicators that you have a problem. So wherever you have a square root, that's you should expect to end up with plus or minus. In fact, remember the quadratic formula, right? It has a plus or minus, and naturally, every time you're dealing with anything quadratic, you might end up with something that is not a function. Okay, so you are solving for y. Well, let's review what has happened here. Very simple relation right here. And then we are decided to find a function for it. Solve for y. We solve for y, and then we ended up with plus or minus. So, and then turns out this is not a function. So, okay, so what do we do about it? Well, there are we'll see other ways to deal with it. But one is this plus or minus allows us to just split the relation into 2. So and each of them will be a function. So y is equal to negative square root of 1 minus x squared, and y equal positive 1 minus x squared. Okay, then these are 2 functions. The plus or minus has been split up, so there will be only 1 output for each input. Okay, so then what remains is just to plot it, to plot them, and to see if we can confirm this picture. Okay, so this is uncomplicated. We may have done this before. Let me go through. Oh, let me pick this one. Maybe this one. Okay. Okay, so this one is. Okay, so we'll do one at a time. So I'll have a bunch of values here. Let's say starting with -1, and here equal to this plus 0.1. So these will be my x's. These are my x's. Okay, and I have a bunch of x's. Okay, maybe a little bit more. Okay, so these are my x's. Ignore the graph. I didn't insert the function yet. Okay, so now let me do it this way. Okay, so let's insert a function here. Y equal, what is it? 1 minus x squared. Okay, so that is our square root. I forgot the square root. Square root. Okay, so that's what I'm going to be doing. So, so literally what you see looking at is pretty much literally what the formula says. Okay, so you see the formula y equals square root of y minus x squared. So I'm going to plug it, enter it for my y's. So this is my y, so it will be a root of what? Of 1 minus x. See the blue square? That's my x, and I'll square it. Close the parentheses. Okay. Okay, let me spread it out. And what the hell happened here? Oh, okay, here it is. Okay. So once again, x's on the x-axis, on the horizontal axis, and then for each of them, I computed y in the next column. Okay, and let me just fix this. Okay, and then I plot each of these points. Each of these points are plotted on the xy plane. You can see them here, and they seem to form a curve. Okay, so I only plotted, 21 points, so that's why it is not, I mean, you can still have your doubts. Is it a curve? Is it made of points? If I plot more points, will they start to form a real curve? And they will if they are big enough, they start to overlap each other. Excel has this extra feature that allows you to see it. It will do it for you what you can do by hand. So it connects those points. The data on the left is only points, but Excel might do it guessing for you, and it will connect those points into something that resembles a curve. Okay? So, but that is one. Let's do the second one. So. Remember, this one will be minus. The same thing, but with a minus. Okay? So, and then I'll be plotting the second one. So, plus or minus. Okay? I spread it down. Now I plot the graph. Oops. So I create a chart for this data. 2 columns of data. The one axis, and then the second version of y. I have 2 y's, remember, so that's why I have 2 columns of y's. So, and as you can see, that column is all negative. No surprise. And so if I plot it, that does look right. What did I do wrong? I'm sorry. Okay, so just a minute. Wrong reference like this. Okay. Okay. So so I have two functions, two charts. Okay, the first one and the second one. As far as Excel is concerned, it doesn't see any difference or relation between them. It was our construction of splitting our domain, splitting our relation into two, and the dependence is we're choosing either positive or negative. So we have to be very specific about that. So for the first column, or the first column is x's, the second column is the first choice of y's with a plus. The third column is the second choice of y, the one with the minus. And as you can see, so the first one plots you upper half of the circle, and then the other one plots the second half of the circle. You could try to sort of move them together if you like. I wish it was more transparent, but if it's not even if it's not transparent, this is pretty much your circle, made of two separate functions. Let me. Okay. Well, as always. Okay. Well, so I just put a different color on the bottom curve in order to see that it is not the same, and we would be as we did, we try to plot the graph over relation. It is pretty hard because there is no such a nice and easy way to plot it. So all you have to plot those two curves, all I had to do was have 21 inputs. 21 inputs quickly gave me 21 outputs. Together, they form 21 points on the XY plane, and we already see with just 21 points, we can see that this is definitely a curve. To complete the curve, I repeated that one more time, and I have the bottom half as well, and so that is definitely a circle. You can imagine what's going to happen if I change what? If I change, like I did over here, this. So I started with 1. If I replace it with 100, what's going to happen to the circle? It's still a relation, the same relation by its nature, but what's going to happen to it has a graph. That graph is a curve. What curve is it? What do you think? Yeah, it will be. It once again it's a circle, but only bigger. So you can actually see if you look at the what I just plotted. It is in fact it runs between -1 and 1. If you accept that it is a circle, what is its radius? 1, right? So over here, this one have radius 1 here. This one will be radius 10. Okay, so they go as squares. So square root of 1 is 1, and that's radius is 1. But if you to get a circle of radius 10, you have to have 100. Okay, so all these circles, they're concentric circles. They will fill the whole plane. Remember how those lines filled the plane when we spoke of the linear relations. So these are kind of quadratic relations, and also these concentric circle will fill the whole plane. Okay, so that's the problem with relations. They are very hard. So let me show you the best we could do with the table before we move on. Where's my table? Oh, here it is. Okay, so as you can see, it's very hard to see that this is a curve. First of all, we had to check not 20 points as we just did, but we had to plot, what is it, 400. This is roughly 400 points. 400 points to examine and to find out whether or not it is on the curve or at least close to the curve, and then we're still uncertain, as you can see. So that is why the switch or progressing from relations to functions is so important. And as you can see, it's not only beneficial, but also there are pitfalls, and pitfalls are here. You might easily end up with more than one function, so you have to watch out for that. So we'll certainly we'll keep coming back to that. At this point, we just say, well, let's study functions specifically. Functions specifically, and the specific idea of a function is that of a black box. Input, and whatever input you put from its domain, it will produce the output y. The only requirement is there is only one y for each x. Okay, so that is why those two functions were not, that relation was not a function, and we had to, the only way to actually understand that, we had to use two functions and study them separately. But as you can see, to study relations or functions, you need to still study functions. Okay, so this is called, as I like to call it, the black box idea of a function. So we don't know what's happening inside. Like this. And it doesn't matter. So sometimes there's a formula, sometimes there isn't. Sometimes there's a description, sometimes there's a graph. We don't know ahead of time what it looks like. Okay, so any questions? All right.